As we said before, luminosity is the total energy output of a star. If you think of it like a light bulb, the luminosity is the star's wattage. We often list a star's luminosity in terms of solar luminosities. In other words, how many times the luminosity of the sun. This is like 3.8 times 10 to the 26 joules per second. A watt is another name for a joule per second. It would make sense to say our sun is a 3.8 times 10 to the 26 watt light bulb. There are a couple of ways of measuring luminosity. One way is useful if you know the flux. This is how much light is produced by each square meter of the star's surface. So that then the whole star's luminosity is just the flux times the surface area. In other words, the bigger the star, the more luminous it is, such as Sirius A and B shown here. Sirius A is much bigger and hence much more luminous than Sirius B.
One way to know flux is if you know the temperature. Stars behave roughly like thermal radiators. Have a look back in Chapter 5 if you don't remember what that is. This means that flux depends just on the temperature. The hotter the star, the more flux it has. These two stars are very different temperatures. You can tell from their colors. Since they're about the same size, the hotter, bluer star is much more luminous than the redder star. Putting those two ideas together, the hotter stars and the bigger stars will be the more luminous stars.
Astronomers have a problem, though. It's not so easy to directly measure a star's surface area. Most stars are so far away that they just look like points of light, even with the best telescopes. So we can't usually use this approach to measure a star's luminosity. We'll see shortly another way we can find the luminosity, using the distance to the star instead. The most luminous stars in the sky have about 1 million solar luminosities, like Eta Carinae, shown here. On the other hand, the least luminous stars are 1 million times less luminous than the sun, such as this faint red dwarf star. In the 2nd century BC, the astronomer Hipparchus created a detailed catalog of stars. He wanted to put them into brightness categories, so he described the brightest stars as stars of the 1st magnitude, and the next brightest stars as stars of the 2nd magnitude, and so on all the way down to 6th magnitude for the faintest stars that he could see. In the last century, astronomers adopted and expanded this approach into the modern system of apparent magnitudes. Rather than just divide stars up into 6 broad categories, we now treat apparent magnitudes as a continuous scale of brightness, meaning that between magnitude 1 and magnitude 2, you can measure magnitude 1.1, 1.2, 1.3, etc.
We've kept the original order the same, so small numbers mean bright stars, and large numbers mean faint stars. The brightest stars have magnitudes around 0, or even go slightly into the negative magnitudes. The faintest stars you can see without a telescope in a dark sky like Hipparchus had in ancient Greece are around magnitude 6. With telescopes and photography, we can see much fainter stars, meaning much bigger numbers. Of course, we can apply the magnitude system to things that are much brighter than stars. For example, the full moon has an apparent magnitude of -11, while the sun has an apparent magnitude of -27. Notice that negative numbers are treated the way they would be on a number line. -27 is a smaller number than -11. The more negative the number, the brighter the object.
Now let's go back to that last idea, how bright a star looks versus how luminous it really is. Apparent magnitude measures brightness, so it depends upon distance. Absolute magnitude is basically luminosity, what the star is really like if distance didn't matter. just like apparent magnitudes. Absolute magnitude is smaller for more luminous stars.
To get the numbers right, imagine you could view all stars from the same distance, 10 parsecs, which is also 32.6 light years. There's nothing very special about this distance. It's just the arbitrary value that was picked when absolute magnitude was defined. Typical absolute magnitudes for stars range from -10 for the most luminous giant stars in the galaxy to 30 for the faintest dwarf stars. A star like the Sun has an absolute magnitude of 5. Remember, this means that if we were 32.6 light years away from the Sun, it would look like a 5th magnitude star in our sky. In other words, it would be faint enough that you would hardly be able to see it in the night sky unless you were far from any city lights. On the other hand, one of those superluminous giant stars with an absolute magnitude of -10 would shine almost as bright as the full moon, even at over 30 light years distance. There obviously aren't any stars like that very close to us, or they'd completely dominate our night sky. Earlier, we saw how we can use parallax to measure distances to stars. Modern technology can let us measure distances to stars that are as much as a couple of thousand light years away. That's a lot of stars, but it still only covers a small part of our galaxy. If we want to measure the distances to stars farther away, then we use these ideas of luminosity and brightness. To say this in magnitudes, we can measure distance by comparing the absolute and apparent magnitudes of a star.
The easy one to measure is the apparent magnitude. After all, that's just how bright the star looks in the sky. We will need other clues to estimate the absolute magnitude. Then we can combine that with the apparent magnitude to get the distance. Remember what we said earlier? Distance, luminosity, and brightness are all related to each other. If you know 2 of these, you can find the third. Since apparent magnitude is tied to brightness and absolute magnitude is tied to luminosity, we can use these 2 to get distance.
Here's the formula that relates them. The distance in light years is 3.26 times 10 to the power of the apparent magnitude minus absolute magnitude plus 5, all divided by 5. I know it looks a little scary, but if you're careful, it's really quite easy to use. We'll do that in just a minute.
In practice, apparent magnitudes are easy to get. That's just how bright a star looks from Earth. However, absolute magnitudes can't be measured directly. They have to be inferred from other things we know about a star's properties. Fortunately, astronomers long ago realized that stars have some predictable relationships between absolute magnitudes and things we can measure, like color and spectra. We'll look more closely at those relationships later in this presentation.
Okay, let's look at how we do this calculation. Here's the formula. The first thing to notice is that everything after the 10 is an exponent. Do this in 2 steps. Calculate the exponent first, then find 10 to the power of that number.
On a calculator, this is where you use that 10 to the x key. You probably have to do some trial experimenting with it, since on some calculators you hit 10 to the x before you put in the number, where on others you hit it after.
The best way to check that is by working through an example. So imagine a star with an absolute magnitude of -5 and an apparent magnitude of 1. Let's calculate how far away it is. We set up the equation, and then we put in -5 for the absolute magnitude and 1 for the apparent magnitude. Notice that we've got a -5, which is just like adding +5. Now add all the pieces on the top, which means the exponent is 11 divided by 5, or 2.2.
Now you've got 10 to the power of 2.2. Estimate the value first. You should already know that 10 to the 2 is 100 and 10 to the 3 is 1,000. So 10 to the 2.2 should be somewhere in between 100 and 1,000. If you didn't know that, go back and review the notes on working with exponents in the math section near the start of the course.
Go ahead and use the 10 to the x key to calculate this. You should get that 10 to the 2.2 is around 158. We're almost there. Now just multiply that by 3.26. This gives you the distance to the star, 517 light years.
We've seen how to calculate distances, but sometimes you don't really need an exact calculation. You just want to get a sense of whether a star is close or far. We can do that easily just by comparing the apparent and absolute magnitudes. First off, remember that absolute magnitude is defined as how the star would look if it were at our standard distance. The apparent magnitude a star would have if it were 32.6 light years away. So if you see that a star has the same apparent and absolute magnitudes, then it has to be at 32.6 light years away.
Next, remember that if a star looks fainter than its absolute magnitude, in other words, if it has a large apparent magnitude compared to its absolute magnitude, then we know it has to be farther than 32.6 light years away. After all, to make it look fainter, you've got to move it farther away.
On the other hand, if the apparent magnitude is smaller than the absolute magnitude, that means that a star looks brighter than its absolute magnitude suggests. That means it must be closer than 32.6 light years away. Lastly, remember that negative values still work like on a number line. So -4 means brighter than -3.
Now it's your turn to try applying the magnitude-distance relation. Here's a star with an apparent magnitude of -1 and an absolute magnitude of -4. First off, is the star more or less than 32.6 light years away? Make sure you can explain your answer. Then go ahead and make the calculation and find out exactly how far away this star is using the magnitude-distance formula.
Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the magnitude-distance section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit.